All right, ladies and gentlemen, welcome back. Here, what we're going to be discussing today is long division with polynomials. Polynomial, of course, is just y is equal to x, or y is equal to x squared, or y is equal to x cubed. It's just some kind of function that has a domain of all real numbers, and uh, the leading term has some, value. Here I have an exponent of 1. It's just kind of looking at it as saying, okay, well, all of those functions are known as a type of, they're called a polynomial because there are many numbers. What we're going to be doing is we're going to be taking a couple different polynomials and dividing them longhand, just like what we did in elementary school. So just some quick vocabulary reminders. The thing that you're actually dividing into is called the dividend. The thing you're doing the dividing with is called the divisor, and the answer is the quotient. And of course, sometimes we're going to wind up with the remainder. Now, what we're going to wind up doing here is there's a process. Again, just like everything in math, there's a process. It's something that you repeat all the time. And so here is where they're kind of telling you what we're going to be doing. We take the leading term of the divisor and the dividend and we compare them and see, okay, well, that's kind of like what we would do in long division. We would take, like, the first number of the dividend and the first number of the number of the divisor, whatever it is, and we'd see, okay, well, how many times will this go into that one? That's kind of what we're going to be doing here. And then once I had, well, okay, well, this goes into it so many times, we would take that value and multiply it by the divisor. Whatever the product is, we'd write it underneath the dividend and then subtract, and then just kind of rinse and repeat until we had completed all of our division stuff that we could do, and we had either a remainder of 0 or some other value as a remainder. And that's kind of what it's telling you here in step 2 or step 3. It says basically just keep doing what you've been doing until you can't do it anymore. And then write out whichever your answer is. So here are two different ways of being able to write your answer. You can say the one on top where we take the divisor times the quotient plus the remainder, which we're really not going to be writing our answer that way. I really kind of like having the answer written this way right here. So that's the way I'm going to demonstrate it, and that's the way I'm going to expect you to show your answer. Whatever the quotient is, we're going to take whatever that is, and then add whatever the remainder is over the divisor, if we have a remainder, because not always will you have one. So let's take a look at it here and see, okay, so this is the first example that we have. Here I have a quadratic expression, which is a type of polynomial, being divided by a linear expression, which is another polynomial. So we set it up just like we would normally set up a long division problem, with the divider inside the house, I guess you could say. That might be what elementary teachers would say, would describe it as, and the x plus 1 is outside the house. But what the first step tells you to do, it says take the first term of each expression and compare them as a ratio. So the first term of the quadratic is simply x squared. The first term of the linear, the divisor, is just x. So if I compare x squared divided by x, that simplifies to just be 1x. Well, that's kind of comparing like the numbers that we would have had before. To say we had a number where the x squared was, well, we would say, well, how many times does the number on the outside go into the number on the inside? And whatever that is what we would write here. So in this case, we wound up with an x. Now, normal long division again says we'll take the x, or take whatever that number is, multiply it to the divisor, and subtract it from the dividend. So, or here, if I say x times x, I get an x squared. And if I say x times 1, I get a plus x. Now what we're going to do is we're going to subtract that. Now here's where you really need to pay attention, because doing long division with polynomials isn't really challenging, but there is a good opportunity, a lot of opportunities to make mistakes with your signs. We're subtracting an expression. So I'm going to put that expression in parentheses to show that we're subtracting these values from each other. So x squared minus x squared, that's 0. 3x squared minus a x minus a positive x, that's the same thing as saying 3x minus x, which gives me 2x's. Then I'm going to bring down the 2, just like we would normally do in long division. And so now I have a new leading term. Now I have a leading term of 2x compared to the leading term of the divisor, which is x. So if I say 2x divided by x, it just simplifies to be a positive 2. So I don't have any more variables left. So you see the number that originally when we started it, we just had x as a, to the first power. So I wrote it over the 3x because we want the powers to kind of match up. So x to the first power with the x to the first power. So the number 2 will go over the whole number that's just the negative 2 of the dividend. So now we will kind of, this is where the rinse and repeat comes in. Take the 2 and multiply it to the divisor. So 2 times x is 2x. 2 times 1 is a positive 2. So again, I'm subtracting an expression, so I put that entire expression in parentheses. And so if I say 2x minus 2x, that's 0. Negative 2 minus 2 is negative 4. So there's nothing left to bring down. So that negative 4, this right here, is my remainder. So x plus 2 happened to be the quotient. The remainder is a negative 4. So if I say plus a negative 4, I'm going to just say minus 4 over the quotient, or I'm sorry, over the divisor, which was x plus 1. So this would be the final solution for this particular problem. Now, it may seem kind of an obscure thing that we're doing here, dividing polynomials. Why would we do it? Well, like a lot of things in math, we take advantage of them on a pretty regular basis without really understanding what we're doing or how it would apply to us. Long division is very much used in cryptography, which you and I probably aren't going to be doing anytime soon. But we all use the internet, and error checking analysis is a very common thing that for data packets as far as electronic communications are concerned. And polynomial division is a very big important part of that. So we may not realize what we're doing with it, but we take advantage of it on a pretty regular basis. So here's our second example. Divide x squared minus 5x plus 6 by x minus 2. Here's the problem set up for us. So again, we're going to take the first term in each expression. So we say x squared divided by x again, and that just simplifies to be 1x. So since that is x to the first power, I'm going to write it above wherever the x to the first power is of the dividend itself. Multiply. X times x is x squared. X times negative 2 is negative 2x. And I'm going to subtract an expression, so I put it in parentheses to make sure I take care of the signs properly. So x squared minus x, that will be 0. Negative 5 minus a negative 2, well, that's the same thing as saying negative 5 plus 2, so that'll give me a negative 3x here. Bring down the 6, just like normal long division would tell you to do. And now let's compare my new leading term with the leading term of the divisor. Well, negative 3x divided by x is negative 3. So that is a constant number, so I'm going to put it over the number of the dividend here, and see we're going to get x minus 3 as the main quotient. Now we're going to see what do we have as a... sorry, I didn't realize that the bells were still ringing. So negative 3 multiplied to the divisor will give me negative 3x here. And negative 3 times negative 2 will give me a positive 6 here. So I'm subtracting the expression. So negative 3 minus negative 3, that's 0. And 6 minus 6 is also 0. So my remainder is 0. Well, if the remainder is 0, that's great. So that means the quotient, x minus 3, is the only thing that we have as our answer, because we don't have to add the 0 if it's a remainder of 0. So now let's move it up a little bit. Let's try a slightly more complicated problem. Here we have a cubic expression divided by a linear expression. So let's see what we wind up doing here. The process doesn't change. Take the leading term of the dividend by the leading term of the divisor. So x cubed over x will give me x squared. So I'm going to place that x squared over where x squared is in the problem and multiply through and see what we get. Well, x squared times x is x cubed. X squared times 3 will be 3x squared. So I'm going to say plus 3x squared here. Make sure everything is lined up. Keep that in parentheses to show that we're subtracting an expression. Keep your signs proper. So x cubed minus x cubed is 0. 3x squared minus 3x squared is also 0. So the only thing that we can bring down, so we have nothing here, but we can bring down the minus 2x and the plus 2. So the leading term that I have left is a negative 2x. And if I compare that with the leading term of the divisor, well, that just simplifies to be negative 2. So I'm going to put that negative 2 over the number in the problem, just the number. So that means that there is no x term by itself. It'll just be nothing. So negative 2 times x is negative 2x. Negative 2 times 3 is a negative 6. Subtract the expression. Negative 2 minus negative 2 cancels out. And that's kind of the whole point. Every problem that we do with long division, that very first one should always make a 0. And now if I say 2 minus negative 6, well, that's going to give me a positive 8. So that right there is my remainder, because there's nothing else to bring down. So the final solution, the quotient, is x squared minus 2 plus the remainder, 8, over the divisor, x plus 3. So that would be the solution to this example. Okay, so here what we're doing is we're changing some things up. What I really want you to pay attention to is really just this stuff right here in the middle. Because what we're doing is we're taking another polynomial that's raised to the 5th power. So we have 3x to the 5th is the biggest value. And you notice from the 5, the next exponent that we see is a 2. So that begs the question, well, where is x to the 4th, x to the 3rd? Where are those terms? And they're not there. But if we have exponent values that are missing, we can't just say, well, that's great. We have to take care, we have to have them represented in some way when we do polynomial division, so that way we can keep the powers of our exponents lined up properly. So if you happen to have a polynomial that is missing some variables, or I'm sorry, some values of the exponents, we have to put zeros in as placeholders for them. So because x to the 4th is not represented in the dividend, we put 0x to the 4th here. Same thing with 0x to the 3rd power. We have to have those placeholders in there because sometimes when we do our division, we'll get a number of that, we'll get a number that uses, or we'll get an exponent, I should say, that uses that number, and we have to make sure that they're lined up properly so that as we do all of our division, all of the exponent values need to kind of, line up from top to bottom as we do all of our work. So here, the process is starting off the same way. 3x to the 5th, the first leading term, divided by x to the 3rd, the leading term of the divisor. So 3x to the 5th divided by x to the 3rd is going to be 3x squared. So I'm going to put that 3x squared over the x squared term of the problem to make sure, again, we want to keep our alignment proper. So 3x squared times x to the 3rd will give me 3x to the 5th. 3x squared times negative 2x will give me negative 2x cubed. So, I'm sorry, not negative 2x, but negative 6x cubed. So we can just, put a 0x to the 4th here if we want to. But you see, if I didn't have that 0x to the 3rd placeholder there, well, we wouldn't be able to combine 6x cubed with negative x squared because they're not like terms. So that's one of the purposes of those placeholders. So 3x to the fifth minus 3x to the fifth is 0. 0 minus 0 is 0. And 0 minus a negative 6 is positive 6x cubed. And then we'll bring down the minus x squared plus x minus 2. We don't really need to bring the whole thing down, but I'm going to go ahead and do it anyway. So my new leading term is 6x cubed divided by the leading term of the divisor, x cubed. Well, 6x cubed divided by x cubed is just 6. So I'm going to place that 6 over the whole number of the problem, which is that negative 2, and now see what we get. So I'll just say plus 6 because it's a positive number. So multiply the quotient to the divisor. 6 times x cubed is 6x cubed. 6 times negative 2x is negative 12x. So I'm going to put negative 12x here. So everything is lined up. And we're subtracting an expression. So we can put 0x squared here if we want. And now let's divide or subtract. 6x cubed minus 6x cubed is 0. Negative x squared minus 0 is negative x squared. X minus negative 12x is a positive 13x, and then we can bring down the negative 2 here. Now at this point, there's nothing else to bring down from the problem, so this whole thing is my remainder. And that's okay. We can have a remainder that looks like that because the power of the remainder, x squared, is less than the power of the divisor, x cubed. So that's okay. So the final way that we will write the answer here is we have 3x squared plus 6 minus x squared plus 13. Well, we'll say plus a negative, I suppose. Minus, or 13x minus 2 over x cubed minus 2x. And so this whole thing would be the final answer. I know it looks a little messy, but it's they usually don't get much worse than what you see right there. So last one here, it's just asking us again to divide x minus 3 into 4x squared, or I'm sorry, 4x to the fourth minus 3x squared plus x minus plus 1. Now you can see we're missing an x cubed term. So 4, 3, 2, 1. So everything is represented except for the x cubed term. So when we write out our problem, we need to make sure that that's there. So I'm going to say x minus 3 is being divided into 4x to the fourth minus 3x. Oops, see, I'm missing it right away. What am I doing? I'm not telling you what to do, and I'm not doing it myself. We have to represent the x cubed term, which is missing. So I'm going to say plus 0x cubed minus 3x squared plus x plus 1. At this point, hopefully you're starting to get the idea of the rinse and repeat thing, taking the leading term of each expression and dividing it, so that way we can see what are we going to wind up working with. So 4x to the fourth divided by x is going to give me 4x cubed. So again, one of the purposes of that placeholder is if I don't have it there, I can't line it up properly. And if I don't line it up properly, we're going to ultimately look like we're going to have a wrong answer. So now that I know what the 4x cubed is part of the quotient, we'll multiply that to the divisor. 4x cubed times x will give me my 4x to the fourth. 4x cubed times negative 3 will give me negative 12x cubed. And again, there's a second reason for that placeholder, because without it, you would wind up writing the x cubed term underneath the 3x squared, and those aren't like terms, so we can't combine them. So here, 4x squared, 4x to the fourth minus 4x to the fourth cancels out. 0 minus negative 12 is positive 12x cubed. And then bring down the rest of the problem, minus 3x squared plus x plus 1. And go through your rinse and repeat cycle. So the new leading term is 12x cubed. Divide that by x, and that's going to give me 12x squared. So we're going to say plus 12x squared here. Multiply through to the quotient, or I'm sorry, to the divisor, and see what you get. So I get 12x cubed here minus 30, oops, I forgot my x squared there, minus 36 x squared. Subtract the expression, so 12 minus 12 is 0. Negative 3 minus negative 36 is a positive 33x squared. And then bring down the x and the 1. And keep going. 33x squared over x simplifies to just be 33x. So we're going to say plus 33x here. Multiply that to the dividend. I'm sorry, to the divisor. 33x times x is 33x squared. 33x times negative 3 is negative 99x. Subtract the expressions. 33 minus 33 is 0. X minus negative 99x is 100x, and then bring down the 1. So we got one more leading term to compare. 100x divided by x is 100. So wow, this is turning out to be a pretty big quotient here. So follow through one more time. Multiply the 100 by the divisor. So 100 times x is 100x. 100 times negative 3 is negative 300. Subtract the expression. 100 minus 100 is 0. 1 minus negative 300 is 301. And so here, there's nothing else to bring down. There's our remainder. All right, so let's go ahead and write this out. I'm going to clean this up just a bit so I can have room to write my answer. So clear all this stuff out because we don't need it anymore. So the final quotient, 4x cubed plus 12x squared plus 33x plus 100 plus 301 over x minus 3. This whole thing works out to be the final answer for this last example. And here we're done. Now, long division is very, very useful for a lot of reasons. Unfortunately, it does take a little bit of time and effort on our parts. It's easy to miss a sign and therefore wind up with the wrong answer. But it works each and every time as long as you're patient with it. Now, we will be getting into something else with division soon called synthetic division, which students seem to like much better, but we'll get there shortly. So make sure you've taken good notes. If you have questions, write them down, bring them to me in class, and we'll see you soon.